So displacement definition, it's the total distance. No, a liar. It is distance from start to finish. It does not matter the path. Okay, so if you started here and you ended here, and like you took this amazing journey of a switchback and you were like ding 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 ding, the displacement is just there to there. That's the displacement. Displacement does not count all your steps. It just is from start to finish, where are you? Speed is a scalar quantity. What does that mean? Scalar. Doesn't have a direction. And it's a measure of how fast. I think I need to go with a thinner pen. So it's a measure of how fast. Oh, I go thinner pen. Does that make it harder to see though, guys? Maybe we'll compromise. Okay, velocity. This is a vector quantity. And this is how fast in a given direction. And acceleration is how quickly the velocity is changing. I don't even know why I turned to cough because I have a mask on. Something to note is that displacement and velocity show which way you're going. So delta x and v show the direction you're going. The sign of acceleration indicates if you're going to speed up or slow down. So if you're speeding up, what are the requirements for velocity and acceleration? They have to have the same sign. If you're speeding up, it's going to be the same sign. If you're slowing down, it's going to be off signs. I need to take the lunch order. I totally forgot to take lunch order yesterday. Today's lunch, it's the egg and cheese bagel sandwich. 1, 2. Trey, egg and cheese bagel sandwich. Who are you waving at? No one? That's just even weirder. Okay. We'll get one extra. Okay. Okay, kinematic equations. These are V equals V naught plus AT. This is just derived from acceleration. Right, acceleration is equal to V final minus V initial over time. The next one was our delta x is equal to V naught t plus 1 half AT squared. And this is just the displacement of an object in a given time. And then the last one, V squared equals V naught squared plus 2a delta x. And this is just the velocity of an object. After traveling the distance x. And so kinematics is with movement with a constant acceleration. If you have a varying acceleration, you can't use kinematics. Most of the time, we're going to say kinematics with our projectiles. Okay. So problem-solving strategy. And this is almost with any situation in physics. The first thing you have to do is draw a picture. how is it moving? This also entails, like in future units, like, are there forces acting on it? Are there initial conditions versus final conditions? Second thing is just list the knowns. With kinematics, convert if necessary. So meaning if you've got like kilometers per hour, what units do you need to be in? Can't be in kilometers per hour. You got to be in what? Meters per second, okay? So keep that in mind. You need to be in meters per second whenever we're doing our units. And then determine what equation you can use. So oftentimes in kinematics, the thing that's tricky is deciding like what is positive and what's negative. And so in general, upwards movement, upwards or rightwards, you have a positive delta x, delta y, and a positive velocity. And then downwards or to the left, you have a negative delta x, delta y, and a negative velocity. And you just should be consistent. Okay, you should just be consistent. And moving in vertical direction. What is the acceleration? Always. Negative 9.8. It's constant. It doesn't change. Moving in a vertical direction, the acceleration is always negative 9.8. On the journey up, on the journey down, it's always negative 9.8. Okay, that is often a trick question in terms of like asking how does the acceleration change? And it's constant. It's always negative 9.8. Mm-hmm. And that is the upper limit. You can definitely have a different value of acceleration. It is smaller. Air resistance will decrease it. Any like constraining forces will decrease it. That is the limit. The fastest an object can fall, the acceleration is negative 9.8. If you add a rocket booster, it's no longer falling. Okay? But the fastest acceleration a falling object can have is negative 9.8. Okay, from there we did projectiles. So let's kind of go here, projectiles. The key thing with projectiles is that you have independent motion. Horizontal movement is independent of vertical movement. And so for a horizontal projectile, like you have this initial x velocity, and then it begins to move downwards, okay? So with a horizontal projectile, there's only a Vx naught. Vy naught is equal to 0, and so the equations you end up using are delta x equals Vx naught t, and delta y equals, I'm going to write it over here. That's my, delta y is equal to 1/2 at squared. Whenever you have horizontal projectiles, oftentimes you guys use the delta y to figure out the time, and then if you know the delta x, you can figure out the velocity, or if you know the velocity, you can find the delta x. You have seen horizontal projectiles time and time again. It's always been like the last part to a situation, right? Where you've got the ball and it's rolling down the incline and it goes to the loop and then it flies off in a horizontal projectile. Or you have this car collides with this car and then they fall off and it's a horizontal projectile. Or you have the pendulum and it's swinging back and forth and it conveniently breaks at the bottom of the swing and it becomes a horizontal projectile. So we have seen this over and over and over again. Expect to see this on the exam where something is flying up horizontally. And the moment you see like flying horizontally or the words horizontal projectile, these should be the equations that you immediately think of. These equations are not on this format of your equation sheet. In your equation sheet, the way it looks is like this. X equals x naught plus v naught t plus 1/2 axt squared. Like that's the format it looks like on your equation sheet. But it simplifies down. If it's a horizontal projectile, it simplifies down in that for the x, the initial x position is 0 and there is no x velocity. For the y, if I just substitute in y values, oops, that's not an equal, that's a plus. If I substitute in my y values, like I don't have an initial y position, I don't have an initial y velocity, and so it simplifies, okay? So the equations are on your equation sheet. They're just not necessarily in the similar format you have. But again, this should be key, horizontal projectiles. If you have an angled projectile, angled projectiles, the initial velocity needs to be broken up. So you have this v naught, vx naught, vy naught. That's some angle. So you are using just geometry, SOHCAHTOA, to figure out what the x and y velocities are. The equations, like they don't simplify. They are the same kinematic equations. They don't simplify. Now you have a y velocity. In terms of kind of looking at this at different positions in the journey of the projectile, at the max, at y max, so when the projectile is here at the top, a couple things to note is that the y velocity is 0. So this occurs at the top. So when I have my delta y max, where I'm at the top, my y velocity is 0. And the time to get up to that position is just half the total time, right? There is that symmetry for projectiles. So the time just to reach that maximum position is just half that time. When it comes back down here at the very bottom, okay, so when delta y is equal to 0, so now we're at the bottom. I didn't format my paper very well. At the bottom, delta y is equal to 0. And so Vy is just actually equal to negative of the initial velocity. And you could think of this in terms of the total time is just twice the time to go up, right? So oftentimes with these types of projectiles, it's kind of easiest to think about the journey up, because I know the journey up, my y velocity at that tippy top point is 0. And so it makes my equation a little simpler. So sometimes it's easier to figure out just what is the time to go up. Okay, total time is just double that. And then if you know the x velocity and you know the y velocity, this total velocity down here is just, right, like this piece right here is just the Pythagorean theorem of what your initial x velocity is, because it doesn't change to whatever the y velocity is. In terms of variations of the problem, if it lands above the axis, so it lands above where it started, my delta y would be positive. If it lands on the axis, so it lands at the same launch height, my delta y is 0. And if it lands below the axis, my delta y is negative. Okay. So those are just some variations in terms of how this looks, how you could kind of extend the problem out. And again, just to kind of compare how the equation looks on your equation sheet. So on your equation sheet, these are the equations that are on your actual equation sheet and the order they're on there. So you have V equals V naught plus AT. You have this X equals X naught plus V naught T plus 1/2 AT squared. And then you have B squared equals V naught squared plus 2A x minus x naught. So that's the formal way it's written on your equation sheet. In terms of looking at it from a projectile point of view, for my x component, my vx is just equal to vx. Like, it doesn't change. If I have no horizontal acceleration, your x velocity doesn't change. This equation, though, simplifies because you don't have, for the x direction, you don't have that acceleration. And the way we kind of think about it is just delta x equals vx naught times t. And this equation, again, doesn't really help us at all. It just says that the x velocity is equal to the x velocity. X velocity squared is equal to x velocity. So again, this is kind of, in projectiles, this is the one that is important for us because we don't have an acceleration in the x direction. The y equations, they don't necessarily simplify, but I want to show them to you in terms of how we've often written them. So we would say this is vy equals vy naught plus ayt. This we just simplified as delta y equals vy naught t plus 1/2 ayt squared. And then the last one, just adding subscripts. But keeping in mind that ay is negative 9.8. We know that, right? And time is the same in both dimensions. So oftentimes you use one dimension to figure out the time, and then you take that time value and plug it into your other dimension equations. Okay. And then the last thing I just wanted to kind of review was graphing, like position time graphs and velocity time graphs for movement, constant acceleration movement. So remember that whenever you're given a graph, the two things that you can get information from the graph are either the slope or the area under the curve. And so kind of key thing is that velocity is the slope of distance time graph. Okay, so velocity is the slope. So if I were to kind of think about this, there's essentially 5 different kind of graphs you could be exposed to, okay, for position time. So if I'm looking at this first graph here, this first position time graph, what could you say about your velocity in this one? What's the velocity in this one? Look at your slope. What's your slope in this one? It's 0. So what's your velocity? Just got to be 0. Okay, so when it's just a horizontal line, your velocity is 0. Let's look at this one. What could you describe about your velocity here? There's 2 descriptors you could give for your velocity. It's positive. It's got a positive slope. And what else? What's the other descriptor you could give about your velocity? It's constant. So velocity is positive and constant. Okay, same kind of vein looking at this one. My 2 descriptors here are my velocity is what and what? Negative and constant. Okay, let's look what happens when we have a curve. A curve on a position time graph. A curve on a position time graph means my slope is changing, so it means my velocity is changing. So clearly I've got some curves here, so my velocity is changing. Let's look at kind of how it's changing. So in this first one, my first descriptor is my velocity positive or negative? It's positive. And is my velocity increasing or decreasing? Is my slope increasing or decreasing? It's increasing. It's going up. So my velocity is increasing. Okay, what if I were to do my descriptors for this graph? For this graph, my velocity is what? It's still a positive velocity. It's still a positive velocity, but velocity is decreasing. Okay, so now I'm going to give you the descriptor. Velocity is negative. Velocity is increasing. Can you draw that? sketch it out. There's my descriptor. Velocity is negative. Velocity is increasing. What would that look like? Velocity is negative. Velocity is increasing. So velocity is increasing means my slope is getting bigger. So my slope is getting steeper, but it's negative slope. Okay, so that means I'm going to be like this. And then what would, I've totally run out of space. I'll do it here. What if I have velocity is negative and velocity is decreasing? What that look like? Velocity is negative, velocity is decreasing. What would that look like? What do you think? Okay, so negative velocity, so I'm still gonna like be going downwards, right? And it's decreasing, so my slope is gonna decrease, so I'm gonna become more shallow. Should look like that. Okay. And so anytime you have a curve on a position time graph, that is going to indicate that I have acceleration. And for velocity time graphs, acceleration is the slope of a velocity time graph. And so it's pretty straightforward. You don't often see velocity time graphs that are curved because usually when we're looking at kinematics, we're looking at situations that have a constant acceleration. But that should be pretty straightforward. And then areas under the curve. So for, I don't want to be in red. I'm still in red. Wish I could just pick up a whiteboard marker. For velocity time graphs, area under the curve is the displacement. And even though we don't often graph them for an acceleration time graph, the area under the curve shows the change in velocity. Luke.
Would it ever ask for displacement of a curve geometry?
Not for this level of physics. So Luke's question, so for my Zoomlanders, Luke asked if it would ever ask you to figure out to calculate out the area under the curve under like a curved graph. It would not ask you to like mathematically calculate it out, but it may be a comparison. So they may give you two graphs and you should be able to conceptually compare the differences between the two. Does that make sense? Okay. Yeah, in a calculus-based physics class, you would. So when you take calculus-based physics in college, that's when you do. In physics 1 and physics 2 are non-calculus based. Physics C is calc-based. There's no A and there's no B. There's physics 1, 2, C mechanics, C, E, and M. So there's actually 4 AP physics tests.
If you justified an answer with any calculus,
that's okay.
Would they give you
yes.
credit for that too?
Yeah.
Okay.
So Zoomlanders, a question was asked if I justified using calculus. Is that fine? You can. Okay, and then the last thing I wanted to remind you of is when we are thinking about experiments with kinematics. So experiments with kinematics, I'm going to remind you of some of the experiments we did. We did the motion sensor with the little car. Do you remember that? Where you had the little car moving towards the motion sensor. Okay, so in that case, I just want to kind of go experiments. Remind you of equipment.
Sorry to interrupt. AAA batteries.
AAA. I know that there is a bunch in that room. Or are they AA?
I have AA. I need AAA.
I feel like they should have triple A. Yeah. Okay, so for experiments, remember you can use a motion sensor. And the motion sensor was this little device. It had this sensor that sent out these sound waves. And what were some of the things you could record with a motion sensor? Because it gives you a graph. Okay, motion sensors give graphs. And what are different kinds of graphs we could... There's the car. What are different kinds of graphs we can create from motion sensor? You can do position time. And it would be like, woo, right? What else could it graph? Even though you didn't have it graph this way, if it can give you position time, what else could it give you? It could give you velocity time, right? It could give you acceleration time. So when you're thinking about experiments and how you could measure things, a motion sensor can allow you to measure position, it can allow you to measure velocity, it can allow you to measure acceleration. Remember, though, how a motion sensor is set up. The object has to be moving towards or away. So when we kind of think about this later on, a motion sensor is not a good sensor to measure circular motion, right? Because if I've got my motion sensor here, it is not capturing the velocity of something rotating in a circle. A motion sensor can really only capture velocity that is like moving linearly. And then the other lab that we did was the bullseye lab. And that's where you shot the projectile off of the table and you used a photo gate. I hate the coloring scheme. So you can use photo gates. And remember, a photo gate is basically this little sensor like this. And an object, a ball, passes through it. And it can measure the velocity. So again, when you're doing your experimental design, and if you're going to use a photo gate to measure something, it has to be something that can pass through the photo gate. When you are talking about your experimental design, recall that you don't have to say, measure the diameter of the object, input that diameter into SparkView, set it to record the velocity. Like, all you have to do is just say, here's my photo gate, it's going to measure the velocity when it goes through. Okay, so like that's your procedure. You don't have to go into the little nuances of the software. And then you could also use timers. You could also use videos to record things like that. Okay. So that is kinematics in 30 minutes. Whew, all of Unit 1 in 30 minutes.